Hello everyone, this is Pure Mathematics Chapter 1, 1.6 Inverse Functions. Before discussing the inverse functions, let us go to the definition of the identity function. So the identity function on a set A is the function denoted by IA, I suffix A, from A to A, defined by IA at x is equal to x. It means every element is mapped to the same itself. So x is mapped to x the same. Such function what we call the identity function. For example, if we take the set A containing elements A, B, C, then IA maps A, the element small a, to itself A. B element is mapped to the same element B. C element is mapped to the same element C, like that. Every element is mapped to the same element. That we call it as the identity function. And if the identity function is on a set A, we call it as, we denote it by I suffix A. It denotes that it is an identity function from the set A to the same set A, which maps each and every element to itself. So image of every element is itself. For example, you can take this function. This is also an identity function where the element 1 is mapped to 1. 1 image is 1, 2 image is 2, 3 image is 3, 4 image is 4. That means every element is mapped to itself. Such functions we call identity functions. If the identity function is on a set A, we denote it by I suffix A. In general, I is the identity function. Let us go to the next slide now. Let us see the definition of inverse function. Let f is from A to B and g is a function from B to A are functions such that if g circle f is equal to identity function on A, that is the composition of g and f is an identity function, and f circle g, the composition of f and g is an identity function on B and the set B, then we say f is the inverse of g. And we write f is equal to g inverse. So f is the inverse of g, means g inverse is equal to f. We write it as f equal to g inverse. The same way, g is the inverse of f. F is inverse of g. Similarly, g is inverse of f. Therefore, we can write g is equal to f inverse. So the important point here is the composition of two functions, g and f, is an identity function. Then we say f is inverse of g and g is inverse of f. Here we can see in the diagram, f is a mapping from A to B and g is a mapping from B to A. If we take the composition of these two, you will get g circle f, because we are applying f first. The composition is g circle f, and g circle f is an identity mapping from A to A, because f is from A to B and g is from B to A. If we take the composition of these two, f and g, you will be getting g circle f is equal to IA. It is an identity mapping from A to A. The same way, g is a mapping from B to A, f is a mapping from A to B. If we take the composition g and f, we say f circle g. Here g is applied first. The function g is applied first. So f circle g is an identity mapping from B to B. So in this case, what you say, g circle f at x is equal to IA at x, but IA is the identity mapping. Therefore, the image of x is the itself, x only. IA at x is equal to x. Similarly, f circle g at x is equal to IB at x. IB is an identity mapping on B. Therefore, IB at x is equal to x. So if g circle f is identity and f circle g is also identity function, then we say g is called inverse of f, and we write f inverse is equal to g, or f is called inverse of g and we write g is equal to f inverse, f equal to g inverse. Both we can say g is f inverse, f is g inverse. And there is another way of defining this. Let g be one-to-one and onto function. Let f be a one-to-one and onto function. That means it is a bijection, we call it as. If it is both one-to-one and onto function from A to B, we say it is a bisection. Then the inverse of f is denoted by f inverse. This is the notation symbol to denote the f inverse. F inverse is a function from B to A such that f of f inverse x is equal to x. That means the composition of f and f inverse is always an identity function. F circle f inverse at x is equal to x. That means f of f inverse x is equal to x for all x in B, or you can say f inverse of fx is equal to x. That means f inverse circle f at x is equal to x. So in either way, the composition of the function and its inverse is always identity. So f circle f inverse is identity. Similarly, f inverse circle f is also identity. In general, we write this way: f circle f inverse at x is equal to x. That means the composition of a function and its inverse is always an identity function. So for a given function f, to find the inverse, we use this equation: f circle f inverse at x is equal to x. This is an important equation. Whenever we want to find inverse of any function, we use this equation. So let us look at an example. Let f is from R to R be a one-to-one and onto function defined by fx is equal to x cube. This is the function given. Find the inverse of f. We have to find what is the inverse of this given function. So as I told before, this is the equation you have to use whenever we want to find f inverse. So let us start. F of f inverse x is equal to x. F circle f inverse is nothing but f of f inverse x is equal to x. And we want to find this f inverse. Since we don't know f inverse, let f inverse x is equal to y. If we let this f inverse x as y, then we will get f of y is equal to x. We keep this inside f inverse x, this term f inverse x as y. Because we don't know this, let us call it as y. Then f of y equal to x. But by the definition of f, fx is x cube. Therefore f of y will be y cube. So y cube is equal to x. If we want to solve for y now, y cube is x. From that, y equal to cube root of x by taking to the power of 1 by 3 both sides. That is, taking cube root both sides to this equation y cube is equal to x, will get y equal to cube root of x. That is x power 1 by 3. Therefore, what is this y? We let y is f inverse x. Therefore, f inverse x is equal to x power 1 by 3. For the function fx is equal to x cube, the inverse function f inverse x is x power 1 by 3. Let us see another example. Let g be a function from R to R which is one-to-one and onto, defined by gx is equal to 7x plus 9. Find g inverse. The same way, we assume first we take the condition, because if g is a function and g inverse is its inverse function, then it is always true g circle g inverse is identity. G circle g inverse is identity. That means g of g inverse x is equal to x. This is always true for any function g and its inverse g inverse. G circle g inverse is always identity. That means g of g inverse x is equal to same x. And now, as we don't know g inverse x, let us put this g inverse x is equal to y. Then g of y equal to x. And from the definition of gx is equal to 7x plus 9, g of y will be 7y plus 9. 7y plus 9 equal to x. If we simplify this one, 7y equal to x minus 9. From that, you will get y equal to x minus 9 over 7. This y is nothing but g inverse x. Therefore, g inverse x is equal to x minus 9 over 7. So this is how you find inverse of this function gx. So in the inverse function, if we observe, in the g function we are multiplying with x, and we are multiplying x with 7 and we are adding 9. Whereas in the g inverse function, we are dividing by 7 and we are subtracting 9. So here in G we are multiplying, in G inverse we are dividing by the same 7. In G we are adding 9, in G inverse we are subtracting 9. So that's how we are getting G inverse X nullifies the effect of Gx. So that Gx and G inverse together, if we take the composition of G and G inverse, we will get identity function. And we have to remember that inverse of any function f exists only when f is both 1 to 1 and onto. When the function is both 1 to 1 and onto, then only the inverse of that function f exists. And you can try to do these two problems in the exercise. If f is from R to R, be a function defined by fx is equal to x cubed minus 9, find the inverse of f. Here fx is a polynomial function and it is 1 to 1 and onto. We can see that this is 1 to 1 and onto. And now you can find the inverse of this function. Same way, another, let g be a function from R to R defined by gx is 6x minus 21, then find g inverse. So you assume that we take the condition that g circle g inverse x is equal to identity. Whenever we want to find the inverse of any function, always we take the equation that f circle f inverse is equal to identity, or g circle g inverse is equal to identity. That means any function and its inverse, if we take composition, we will be getting identity function. So this is the end of this presentation on inverse functions. Thank you.